Hi, my name is Patty and I'll be introducing my teammates, which are Angie, Anacaro, Santivias, and myself. The four of us created a project for calculus, which was a water rocket.
Well, so these are the mathematical formulas that I used. So I wanted to find acceleration because it was the only thing the tracker didn't give me. So I assigned it a variable and I integrated to get the function of velocity. Acceleration integrated is equals to this. This is the initial condition for C. So after I needed the position function, so I integrated again the one for velocity and to get the position function. This one is position. The initial position, I just crossed it out because I am assuming, thanks to my point of reference, that the initial position is 0. So after doing all the integrating from acceleration to position, I just did substitution with the data the tracker gave me. I used final velocity, time, and then initial velocity in each of the cases. This is distilled, potable, salt, and mineral water. In each cases, I got an acceleration and also a position in meters in the horizontal line. So yeah, this is a way we can applicate calculus in everyday life. We can just applicate a formula and take it into numbers that could help us estimate the acceleration of a bottle. This is considering that the conditions are perfect. I mean that we have no air resistance and no other physics phenomena that is affecting our results. So yeah, basically this is considering a perfect condition environment. So if the results differ from the real acceleration for a little bit, it's maybe because of that, because we are not taking account the numbers that affect every physical phenomena that affect the results. And yeah, so I integrated acceleration to velocity and then velocity to initial position. Then I substituted, got acceleration and displacement in the horizontal line for every type of water.
So there are two objectives that we want to have. The first one is to actually find the measurable water with a bottle so that it works and can fly. The second one is to find how much, with which different types of water does it actually go faster and higher. So we will evaluate with mineral, salt water, the water that we drink, and distillate it to find this answer, with which one it's actually better to go faster and higher. The hypothesis is that the mineral water will be faster, stronger with acceleration and velocity, and the highest. This is because it has more carbon dioxide than the other ones. Therefore, it has a different pressure from the atmosphere, which will make it go faster than the other ones.
The materials used for this experiment were the following: a plastic bottle, but keep an extra one as well, a cork to seal the bottle, also have an extra, a long needle to make a hole in the cork, a bike pump to pump air into the bottle rocket, and 200 milliliters of each water type: potable water, distilled water, water with salt to imitate seawater, and mineral water. Now, why did we choose these types of water? First, we chose normal water because water is an universal solvent due to its polar characteristics and its capacity to form hydrogen bridges with other ionic polar substances. Also, we chose distilled water because it is prepared by boiling it, which pulls the minerals out of its chemical composition. Also, distilled water can also leach plastic if it is stored in a plastic container for a long time, and we thought it would be interesting to try this type out. We also chose water with salt because it will be a lot like seawater, which has a really wide range of different minerals and chemicals such as magnesium, sodium, and sulfur. We chose carbonated water because it contains carbonic acid, which starts to decompose and freeze carbon dioxide in bubbles if that liquid is depressurized. Thanks to this, we believe that when it meets the lower pressure of the atmosphere, it will propel the rocket more.
The procedure we had to follow was we needed water bottles, and first we grabbed 1 liter Coke bottles, but it didn't work because the bottle was too big, and we tried to fit the air pump, you know, the little needle of the air pump in the cap of the water bottle, but it was a complete fail, it didn't work. So then we had to try again with a 500 milliliter water bottle. We filled it up with water and salt, simulating ocean water, with sparkling water and oxygenated water and regular water. So we tried 4 types of water, and we had to change the way we put the needle in the bottle. The second way we tried was to put it on the side, but it was also a fail because it didn't seal correctly. So it was fail and try again and fail and try again until we managed with a cork. We poked the hole in the cork, put the cork in the opening of the bottle where you drink, and we sealed it with tape. And that way when we put the air in it, it could launch properly. So the process was filling the water bottle with the type of water we wanted to try, putting the cork in the needle and sealing it up, and then pumping the air. We had to do a certain angle, and we noticed that for a parabola we had to put it almost straight up, because if we put it like in an incline, it would go straight, like the pumping the air. We had to do a certain angle, and we noticed that for a parabola we had to put it almost straight up, because if we put it like in an incline, it would go straight, like the parabola would be a small parabola, and if we put it up, it would go like this. And yeah, so we had to connect it, pump, and it would shoot out like a rocket. And to tape the videos, we had a tripod, and yeah, that's basically the procedure.
The results were the following. In the distilled water condition, the initial velocity was 0.025 meters over second, the final velocity was 0.71 meters over second, and the maximum height was 0.42 meters. In the potable water condition, the initial velocity was 0.11 meters over second, the final velocity was 4.14 meters over second, which was the greatest velocity out of all conditions, and the maximum height was 1.54 meters. In the condition of water with salt, the initial velocity was 0.008 meters over second, the final velocity was 2.82 meters over second, and the maximum height was 1.57 meters. In the mineral water condition, the initial velocity was 0, and the final velocity was 3.94 meters over second. The maximum height was 1.94 meters, which was the highest height out of all conditions.
Conclusions. So from our calculus, we got that mineral water was not the strongest one, not the one with the higher velocity or the higher acceleration. That one was potable water. Potable water had the highest acceleration and the highest velocity. So our hypothesis said that the mineral water would be the strongest one, and it wasn't, so it was refuted. I believe that this refutation happened because of the lack of control of extraneous variables. So maybe if we had control more the extraneous variables, like the number of pumps, the amount of water, and the air resistance, maybe the results would have gotten our hypothesis. The one meaning that the mineral water is the strongest one thanks to the depressurizing of the pressure in the bottle and outside the bottle. But meanwhile, it was refuted our hypothesis.